Hello students, welcome to my YouTube channel Dear Mathematics and also welcome to the chapter of set. In the previous video, we have already discussed about different types of sets, then subsets, proper subsets, representation of sets, and also some of the different types of sets belongs to the set chapter. In this particular session, we are going to discuss about the Venn diagram and then the operation on sets, likewise union of sets, intersection of sets, difference of sets, etc. etc. So first of all, let us go to the Venn diagram. What is the definition of Venn diagram? Why we should call it as Venn diagram? So first of all, Swiss mathematician Euler gave an idea to represent a set by the points in a closed curve. Then later on, British mathematician John Venn brought this idea to practice. That is why this diagram is called as the Venn diagram, or you can say that Venn Euler diagram. So what are the Venn diagrams? Suppose A is a set, and all of the points in a set are represented by this closed curve. This is a closed curve, and here it is the U is the universal set for this is set A. Similarly, let us take two sets in between in a universal set. This sets can be like this, or this sets can be like this. One set is a subset of another set, or you can they intersect each other and they have some common parts and they are belongs to a same universal set. So these are some of the fundamentals behind the topic Venn diagram. So later on we have to go through the operation on sets, and here we have to use these Venn diagrams to represent these sets. Okay, let us go through the operation of sets. So before going to operation on sets, let us discuss about some of the fundamentals that we have to discuss in this operation on sets. And first one is union of sets. Then second one is intersection of two sets. You can write down union of two sets, intersection of two sets, then disjoint sets, pairwise disjoint sets, difference of two sets, and then in the sixth number symmetric difference of two sets. And in the last part, a complement of a set, and we have to represent all of the seven fundamentals by giving the definition, example, and the Venn diagram. So let us discuss from the first part, that is the union of sets. So first of all, let us discuss about the first fundamental operation of the operation on sets, and that is union of sets. Let A and B be two sets, then the union of A and B is the set of all those elements which lies either in A or in B, and it is denoted in the symbol A union B. It is the representation of the A union B, and it is read as A union B. Then symbolically in set builder method we can write down, or we can represent the union of A and B in this form X, such that either X belongs to A or X belongs to B. Clearly, these notes are very much important for the problems based upon the chapter set. So if X belongs to A union B, that means X lie either in A or in B. Suppose X does not belongs to A union B set, that means X does not belongs to A and also X does not belongs to B. Here is the difference in between these two lines. In the A union B, whenever X belongs to A union B, we are writing here OR. Whenever X does not belongs to A union B, we are writing out AND. So these are the fundamental parts of the union of two sets. Then moving towards to the representation of union of two sets in the Venn diagram method, and then going for some of the examples. Then let us discuss about the representation of union of two sets by the Venn diagram. The shaded region is A union B, that means we will draw some of the Venn diagrams here, and the shaded portion will be the notation of or the representation of the A union B. And I have taken three categories here. The first category is here, neither A subset of B or nor B subset of A. In the second case, one set is subset of another set. And in the third number category, I have taken A and B are disjoint sets. So there can be three possibility of the categorization of the A union B. So let us discuss about the first case here, and let us draw the universal set. Neither A subset of B nor B subset of A, that means this Venn diagram can be like this. And this is the universal set. And here it is the A set and B set, and we have to choose all of the elements either in A or in B. That means it will be consist of, or it will consist in similar manner, and we have to take, or we have to consider all of the elements that are present either in the set A or in the set B. And I have written here the shaded region is A union B in the following diagram. So here is the first diagram where neither A set is subset of B set nor B set is subset of A set, and here it is the representation of A union B, and these shaded persons are representing the A union B set. Let us moving towards to the second number of case where the condition is like this: one set is subset of another set, that means the A set is subset of another set. Here it is the set A and is the set V, and this is the universal set. Both of the A set and V set, here also A set and V set, are the subsets of universal set. That means they are present in the universal set. U is the universal set for the two sets A and V, and here we have to find out the union of A and V as A subset of V. Here the A union V must be equal to B. If B subset of A, that means if B lies in the set A, or A is the superset of B, then A union B will be equal to A. This is the second category for the finding out of the A union V. Then moving towards to the case number 3, where A and V are two disjoint sets, and I have taken here two disjoint sets A and V, and here it is the universal set U for the two sets A and V, and the shaded person or shaded region represents the A union V as their disjoint. Disjoint means their intersection must be equal to 5. A intersection V is equal to 5. So these are all some of the representation of the union of two sets by using the Venn diagrams. Let us moving towards to the some of the problems based upon the A union V. Union of sets, when the number of sets is more than 1. So in such type of cases, we have to denote in a special type of symbolization, and that is union of AI, where I is from the set number 1 up to the set number n. That means I have taken here A1, A2, A3, an are finite n number of sets, and their union is denoted by A1 union A2 union A3 union an. Then let us go solve some of the examples. This is the example number 1 based upon the type number 1 or case number 1. So, and here we have to discuss neither A subset of V nor B subset of A. So here let A is equal to 1, 2, 3 and V set is equal to 3, 4, 5, and you can see that neither A subset of V or nor V subset of A. In such type, A union V can be evaluated by this 1, 2, 3 union 3, 4, 5, and this is 1, 2, 3, 4, 5. This is the set A union V. Then moving towards to the example based upon the second type, where one set is subset of another set. Suppose A set is subset of B set. Let A set is equal to 1, 2, 3 and V set is equal to 1, 2, 3, 4. Here A union V is equal to A set, it is 1, 2, 3. Then union V set 1, 2, 3, 4. Then this union will be 1, 2, 3, 4. And which is equal to the V set. And already we have studied a little while ago A union V is equal to V when A set is the subset of B set. Then moving, this is the example number 2. Then moving towards to the example number 3 based upon the category or case number 3 of the operation of sets, where A and V are two disjoint sets. Example number 3, A and V are two disjoint sets. Let A is equal to 1, 2, 3 and V set is equal to 5, 6. Disjoint set means they have no common elements. You can write down, they have no common elements. And here A union V is equal to 1, 2, 3 union 5, 6, and here the union will be 1, 2, 3, 5, 6, set of the elements 1, 2, 3, 5, 6. So this is all about the first fundamental of operation on sets, and that is union of sets. In the next page we are going to discuss about the intersection of sets. Then coming towards to the intersection of two sets, let A and B be any two sets. The intersection of A and B is the set of collection of all those elements that lies in both A and B. It is denoted by the symbol A intersection B, and it is read as A intersection B. It is the symbolized form. Symbolically, in the set builder method, we can represent the intersection of two sets as A intersection B is equal to X such that X belongs to A and X belongs to B. That means it will lie both in the set A and as well as in the set V. Then clearly, if X belongs to A intersection B, that means X lies in both the parts. That means in the first set as well as in the second set. But whenever X does not belongs to A intersection B, that means X does not belongs to A or X does not belongs to B. You have to be careful about the two words and here it is or. Whenever X belongs to A intersection B, then X belongs to both. X belongs to A set and as well as the second set B set. But whenever X does not belongs to the A intersection B, that means the common part, that means X does not belongs to A or X does not belongs to B. Then let us move towards to the representation of A intersection B in the Venn diagram method. Then moving towards to the representation of intersection of two sets A and B in the Venn diagram method, and I have categorized the A intersection V into three sections. I have classified them into the three sections, and the first one is neither A subset of V nor B subset of A. The second one is A subset of V, and the third one is A and V are disjoint sets. That means they do not have any common element. They have no common element. They have no common element. Okay. So we will draw three Venn diagrams for the three cases, and the shaded region will be the final solution or it will be the intersection of A and V. So for A and V, I am taking U as the universal set. That means both A and V lies in the universal set. Here neither A subset of V nor V subset of A, and the solution will be the common parts between A and V, and here it is the A intersection V. Here it is the A intersection V. Now moving towards to the second case, second section, here A is subset of V. Here it is the set A and here it is the set V, and we have to find out the common elements between the two sets A and V, and these are the common elements between A and V, because these regions, these shaded regions are present as well as in the A as well as in the V set. So here A intersection V is equal to A set. You have to remind, if B subset of A, then in this case A subset of V is equal to B set. Then moving towards the last section or last part of the intersection of the A and V. Here both A and V are two disjoint sets. That means they have no common elements. It is the universal set U, and as there is no common element between A and V or no common person between A and V, so here A intersection V is equal to 5. So here we cannot find out any shaded region in the intersection of A intersection V. So intersection V is equal to 5. So it is all about the representation of intersection of two sets by Venn diagram. Then let us come towards to the examples or problems based upon the intersection of A and V. Now we are going to discuss about the intersection of more than one sets, more than two sets. Suppose I have taken here n number of finite sets that are A1, A2, A3, an, and we have to find out the intersection of all n finite sets, and this can be denoted by intersection of AI. Here I is placed for all of the numbers from 1 up to n, and it is defined as A1 intersection A2 intersection A3 intersection an. That means we have to find out the common part in between or among the all n finite sets, and that will be the intersection of more than two sets. Now let us solve some of the problems based upon the intersection of sets. The first example is based upon neither A subset of V nor B subset of A. That means the first part or the first category of the intersection of two sets. Let A is equal to 1, 2, 3 and V is equal to 3, 4, 5, and we have to find out the intersection between the two sets A and V, and it will be intersection of 1, 2, 3, the set of 1, 2, 3, then intersection with the set of 3, 4, 5, and the common element is 3. So here A intersection V is equal to 3. So here it is the answer of A intersection V, and it is based upon the fundamental neither A subset of V nor B subset of A. We have already discussed it in the Venn diagram number part 1. Then moving towards to the example number 2, where A is a subset of V. That means the second section or the second part of the categorization of the intersection of two sets. Let A set is equal to 1, 2 and V set is equal to 3, 4, 5. And we have to find out the intersection of A and V, and the intersection will be intersection of the set of containing elements 1, 2 and the elements, okay, this will be the 1, 2, 3, 4, 5, because we have taken it as A subset of V. So here you can see that A is subset of B, intersection with 1, 2, 3, 4 and 5, and the common elements are 1 and 2. So here it is the solution. The intersection of A and V, it is the set of containing the elements 1, 2, but it is the set A, and we have already discussed it about the A subset of V in the Venn diagram number 2. Then moving towards to the last example that can be based upon the intersection of A and V, and let here A and V are disjoint sets. Disjoint sets means they have no common elements. So let A is equal to 1, 2 and V is equal to 5, 6, and here A intersection V is equal to 1, 2 intersection 5, 6, and the intersection of A and V, it is 5. So here it is the final solution of A intersection V, and we have categorized and we have classified the three examples based upon the three Venn diagrams of A intersection V. And the first one is neither A subset of V nor B subset of A. The second one is one set is subset of another set. Then their intersection will be the smallest set, that which is the subset of another set. Then in the example number 3, which is based upon the Venn diagram number 3 also, that means A and V are two disjoint sets, that means they have no common elements. In that case, we are getting the resultant or the intersection of A and V, that means intersection of two sets as 5. So here it is all about the intersection of two sets. Next, moving towards to the complete definition and fundamental of disjoint sets. So here it is the definition of disjoint sets. Two sets A and B are said to be disjoint if A intersection B is equal to 5. We have already discussed it in the Venn diagram of A intersection B. Let us Again, take the Venn diagram, and here it is the universal set U, and these are the sets A and V are subsets of the universal set. If they have no common element, that means A intersection B is equal to phi. In that case, we can say that A and B sets are two disjoint sets. Suppose they are not disjoint sets. If A intersection V is not equal to phi, suppose in that case, suppose they are intersecting and their intersection is not equal to phi. Here it is the set A and V that are subsets of the universal set U. In that case, if A intersection V is not equal to phi, then A and V are said to be intersecting or overlapping sets. Here in this case, we can say that A and V, suppose I have taken these sets as C and D, so you can say that C and D are overlapping sets. Overlapping sets. But here in this case, you can say that A and V are disjoint sets. Disjoint sets. So this is all about the definition and fundamental behind the disjoint sets. Then let us solve some of the problems based upon the disjoint sets and overlapping sets. Let A is equal to 1, 2, V is equal to 3, 4, and C is equal to 4, 5. Here A intersection V is equal to intersection 3, 4, and this is equal to 5. And so A and V are disjoint sets. Now let us find out V intersection C. 3, 4 intersection 4, 5 is equal to 4, and that is not equal to 5 because we are finding out a common element 4 which is present both in the set V as well as in the set C. So here in this case we can say that V and C are overlapping or intersecting sets. So it is all about the disjoint sets and overlapping sets, or you can say that intersecting sets. Then let us move to the pairwise disjoint sets. Then let us move to the pairwise disjoint sets, a family of sets A1, A2, A3, dot dot An. That means we have taken n number of sets and there are more than 2. Is said to be pairwise disjoint family of sets if no two members of sets have a common elements. Okay, thus the family of sets A1, A2, A3, dot 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 An is said to be pairwise disjoint sets if AI intersection AJ is equal to phi. Okay, let us make the statement or the definition very simple. Let A, B and C be any three finite sets. Then if A intersection V, B intersection C, C intersection A is equal to phi, then we can say that the three sets A, B and C are pairwise disjoint sets. That means we cannot get any common element in between any two sets. You can take A and V, you can take V and C, or you can take A and C. And the representation in the Venn diagram, you can mention it as A, B and C. And they are very much different from each other. And no two sets out of the A, B, C intersect with each other. That means A does not intersect with V, B does not intersect with C, and C does not intersect with A. In this case only, we can say that the three sets, or you can take it as more than three, you can take it as 4 A, B, C, D. Here this is A, B, C, D, and they does not intersect or they do not intersect each other. That means A do not intersect with B, B do not intersect with D, D do not intersect with C. No two sets, no two finite sets intersect with each other. That means in this case we can say that, or it is a possibility of, or it is a definition of pairwise disjoint set. And let us take some of the example based upon the pairwise disjoint sets so that it will be very much clear about you. Let A is equal to 1, 2, B is equal to 3, 4, and C is equal to 5, 6. First of all, we have to find out A intersection B. 1, 2 intersection with the set of 3, 4, and you cannot find out any common element between A and B, so it is equal to 5. Similarly, B intersection C, it is 3, 4 intersection 5, 6, it is also equal to 5. Then another exists there, A and C. So considering A and C, A intersection C, it is equal to set of elements 1, 2 intersection with set of elements 5, 6, it will also give the result as 5. So all of the results are 5. So in this case we can say that, so the three sets A, B and C are pairwise disjoint sets. Pairwise disjoint sets. These three sets are pairwise disjoint sets. So it is all about the definition of pairwise disjoint sets and the fundamental and the representation in Venn diagram as well as the problems based upon the pairwise disjoint sets. Then let us move towards to the difference of two sets. Then coming towards to the difference of two sets, let A and B be to any two finite sets. The difference of A and B is the set of all those elements which are present in A but do not present in B. Let us take a diagram, Venn diagram. Here it is the universal set U and the two sets A and B. Here they intersect each other. The elements those are present in the set A but do not belong to the set B, and these persons, the shaded persons, represents the A difference V, and it is denoted by A difference V. It is read as also A difference V. Symbolically, A difference V in the set builder method can be denoted or defined as X, such that those elements which are belonging to the set A, X belongs to A, and those elements X do not belong to the set B. Similarly, if we are taking or we are trying to finding out the difference of B and A. So it will be denoted by V difference A, and it is defined as V difference A is equal to X, such that X belongs to B and X does not belongs to A. Then moving towards the difference of two sets, let A and B be any two finite sets, then the set of those elements which are present in A but do not present in B is called as the difference of A and B. It is denoted by the symbol A difference B, and it is read as A difference B. And we can also represent it in the Venn diagram method. This is the universal set A, and suppose I have taken two intersecting sets A and B, so that it will be easy to understand what is A difference B in the diagrammatic method. Those persons which are present in A but do not present in the set B, and these are called as this person, this shaded person or shaded part, you can say that this is called as the A difference B. Suppose we are trying to find out the difference of B and A, and it will be denoted by V difference A, and this is shaded person will be defined as like this A and B. Here it is the universal set U, and this shaded person or shaded part which are belonging to the set B but do not belong to the set A, so it is called as V difference A. But in the set builder method, you can also define the difference of A and B like this. A difference B is equal to the set of those elements which are counted as X, which are belonging to the set A but does not belong to the set B. Similarly, we can also symbolically we can also define V difference A in the set builder method, and these are X such that X belongs to B and X does not belongs to the set A. So this is all about the difference of two sets and some of the fundamentals and their representation in Venn diagram method. Then let us come solve some of the problems based upon the A difference V and V difference A. Let us take two sets A and V, two finite sets, so that it will be easy to calculate the A difference V and as well as the V difference A. Let, this is the example, let A set is equal to 1, 2, 3 and V set is equal to 3, 4, 5. Here A difference V is equal to 1, 2, 3, difference 3, 4, 5. And here it is the set 1, 2 and this is A difference B. Just we have to find out the elements which are present in A but do not present in B. You can say that this 3 element is present in the set B. So it will be not counted. So these are the 2 elements 1 and 2 which are present in the set A but do not present in the set B. So here it is the answer, set of the containing elements 1 and 2. Similarly, finding out the value or the set of V difference A, it will be 3, 4, 5, set of 1, 2, 3 and you can see that 3 element is common to both V and A. Just we have to find out those elements which are present in V but do not present in the set A, and those elements are 4 and 5. So set of the elements 4 and 5. So here it is the V difference A. So it is all about the difference of two sets. Now let us discuss about the symmetry difference of two sets. Let A and B be two sets. The symmetry difference of A and B, it is union of the A difference V and with the V difference A. And this is the representation in the Venn diagram method. Just we have to find out the A difference V and V difference A, and then we have to find out their union. And this, it is denoted by A delta V, and A delta V is defined as the union of A difference V with V difference A. So A delta V, otherwise in alternative method we can also express it in the set builder method, and this is the X such that X does not belongs to the A intersection B. That means just we have to exclude those parts which have the common parts of A and V. So, and this is just from the A union V, just we have to exclude the A intersection V, and this is the A delta V or the symmetric difference of A and V. Then let us take an example so that it will be clear. Let A set is equal to 1, 2, 3 and V set is equal to 3, 4, 5. Then first of all we have to find out A difference V. It is 1, 2, 3, difference 3, 4, 5. This is 1, 2. Just we have to find out those elements which are not present in the set V. Then we have to find out V difference A. That means we have to find those elements which are present in V but do not present in the set A. That means 1, those elements are 4, 5. Then we have to find out the symmetric difference by taking the union of A difference V with the V difference A. So A delta V is equal to union of A difference V and V difference A, and this is 1, 2, set of elements 1, 2 with the set of the elements 4, 5, and this is the resultant answer. This is 1, 2, 4, 5, and here it is the symmetry difference of A and V. So it is all about the symmetric difference of two sets A and V. Then let us discuss about the complement of a set. This is the last phase of this particular video session, and that is complement of a set. The complement of a set A is denoted by A to the power C or A dash, and it is the collection of all those elements present in the universal set U which are not belonging to the set A. Let us take a Venn diagram first. This is the universal set U, and here it is the set A which is subset of the universal set U. We have to find out those elements which are not present in the set A. That means the rest of the elements are here. And this shaded person is called as the complement of the set A. And this can be represented as or denoted by a to the power c, or also we can take it as a dash, and we can find out why u difference a. Just we have to different the set a from the set u. So it is denoted by the a to the power c or a dash. Let us take an example so that it will be very much clear to you. Let the universal set as 1, 2, 3, 4, 5, 6 and a is equal to 5 and 6. Then we have to find out a complement or the complement of the set A, and it is defined as u difference A, and it is 1, 2, 3, 4, 5, 6 difference A set, that is 5, 6. And we have to find out only those elements of the universal set which are not belonging to the A set. That means those elements are 1, 2, 3, 4. So the final answer or the complement of the set A is here, and this is the set containing the elements 1, 2, 3, 4. So in this particular session we have discussed about the Venn diagrams, then the operation of sets, and we have seen 7 operation on sets are there: union of two sets, intersection of two sets, difference of two, complement of a set. In the next video we are going to start some of the important theorems that are based upon the chapter set. Till then, thank you.